8.2, modeling engineering applications by linear systems of ODEs. In this topic, we will work on two application questions. We just apply what we learned in 8.1, then we use the linear system. We solve the problems by solving linear systems of ODEs. Yeah. All right. It's pretty simple. Yeah. But we need to get used to this new method. Yeah. All right. Yeah. So let's look at the question first. Problem number 12. Mixing problem involving two tanks. Yeah. Remember, we did a mixing problem with one tank before. Yeah. Remember the one physical law we used, balance law, right? Yeah, balance law. Yeah. So that same topic. Yeah. But this time we have two tanks. Yeah. So it's a system of tanks. Yeah. So let's look at the question first. Yeah. So the figure looks like this. T1, T2, two tanks. Yeah. Tank T1 and T2 in the figure contain initially 100 gallons of water each. Yeah. Yeah. T1, pure water. T2, 150 pounds of fertilizers dissolved in T2. Yeah. By circulating liquid at a rate of 2 gallons per minute. Yeah. So here you can see the figure, the flow direction, yeah, from left to right, right to left, yeah, circulating in that way. Yeah. And the stirring, yeah. The stirring here, we mean in each tank, we do that stirring to make the mixture uniform. Yeah, each tank. Okay. Yeah. But the concentration in two different tanks should be different. Yeah. All right. Then the amount of fertilizers Y1 in T1 and Y2 in T2 change with time. How long should we let the liquid circulate so that T1 will contain at least half as much fertilizer as there will be left in T2? Yeah, half. We just want to find that point. Yeah, yeah, half point. Yeah, so that is Y1 equals 1/2 of Y2. But we need to find that time, that special time point. Yeah. If I write a formula, it should be like this. We need to find little T1. Yeah, let's say. Oh, I touched something. Yeah. All right. Yeah, here, let me adjust the position carefully. Yeah. Because the screen, the touch screen is very sensitive. If I touch somewhere, yeah, something could be wrong. Here, let me use some cloth to avoid my screen touch thing. Yeah. All right, protect a little bit. All right, so we need to find that special T1 point. T1, some special T1, such that Y1 function of T1 equals 1/2 of Y2 function of T1. But we need to find this little y1, little y2 functions first. Yeah. All right. Yeah. So that's the question. Yeah. So let us. Yeah. Initial condition. Yeah. That's obvious. Yeah. initially, the amount of fertilizer in T1 is 0. The amount of the fertilizer in T2 is 150 pounds. Yeah. Solution. Yeah. The physical law we need to use, the balance law. Okay? But the question, how to use the balance law on the 2 tanks? Yeah. This time, it's different from our 1 tank balance law. That's pretty straightforward. 2 tank, you just use the same way as the 1 tank way. Yeah. Here, you can draw a line to separate these 2 tanks. Okay? Yeah. You know, imagine a line, you know, cut off, separate 2 tanks. Then for each tank, you can apply balance law, right? Inflow, outflow for T1, and also inflow, outflow for T2. Yeah. So you can write 2 equations. Yeah. So let's do the T1 equation first. Yeah. T1 equation, we need the balance law version, y1 prime equals inflow 1 per minute, the rate, yeah, inflow rate, yeah, minus outflow 1 with respect to T1, yeah, outflow. Yeah. With respect to T1 inflow, that's this part, right? Yeah. Yeah. And, you know, this direction. With respect to T1 outflow, that direction. Okay? Yeah. So we can, similarly, for T2 tank, Y2 prime, the rate of change of the amount of fertilizer function in T2 tank. Yeah. But inflow with respect to, yeah, this is the inflow, okay. T2, yeah. Outflow T1, right? Outflow, okay? Yeah. So that's pretty straightforward. So we can establish 2 linear equations easily. Yeah. Okay. All right. Yeah. The inflow, but we need to figure out inflow rate, outflow rate for each tank. Yeah. The inflow rate, yeah, because the 2 gallons per minute, right? Yeah. Yeah. And because here, in each minute, so let's the rate, look at the rate in each minute. In each minute, 2 gallons of mixture flows into the T1 from T2, yeah. But that 2 gallons, that's 2 gallons of 100 gallon, right? Yeah. So the, you know, total quantity of the mixture in T2, that's 100 gallons. So from the total 100 gallons in T2, 2 gallons of it flows into the T1. Yeah. So that's the rate. So the rate, yeah, yeah, the rate. So 2 out of 100, right? Yeah, that portion. Yeah, 2 out of 100 of Y2. Yeah, because the total amount of fertilizer in T2, that's Y2. Yeah, but you only let it flow out 2%, right? Yeah, 2 gallons, that's 2%, okay? Yeah. So only 2% of the Y2 amount flows into T1 per minute. That's the rate, yeah, per minute. All right. Similarly, outflow, 2% of Y1 amount from T1, right? Yeah, flows out. Yeah. So minus that amount. Okay. All right. Similarly for y2 prime, yeah, flows in. Yeah, that's 2% of y1 flows in. Yeah, flows out 2% of y2 amount flows out. See? Yeah, just opposite. Okay. Yeah, opposite direction. Yeah. Then, so this is our linear system. So you can see we get a simple linear system. Yeah. So let's write linear system out. Yeah. Yeah. So this time we need to solve this simple linear system to find a solution. Yeah. Okay. Yeah. Yeah. All right. So the next question: how to solve this linear system? Yeah. Yeah. Here we can use two ways. Yeah. The first way, yeah, we just use the algebra directly, so without using any special knowledge, yeah, because these are two equations. Yeah. So we just solve these two equations, use the straightforward algebraic manipulation. Yeah, the first. But the second way, we will use the method we developed from 8.1. Yeah. So we compare. Yeah. Although the same result, but you can see how different these two methods could be. Yeah. All right. Yeah. The first, by observation, can you see something, the special property, these positive 2% of y2, negative 2% of y2. If you add these two equations up, both sides, you have a cancellation, right? Positive, negative, same amount, cancellation. Similarly, negative 2% of y1, but the positive 2% of y1. After you add them up, you cancel out. So both terms cancel out. The right-hand side becomes 0. Yeah. So you get a y1 prime plus y2 prime equals 0. Yeah. The special property. Yeah. All right. Yeah. So the derivative of y1 plus derivative of y2 equals 0. Yeah. Because derivative, we know, it has the linearity property, right? Yes. That means we can write y1 plus y2 prime equals 0. Yeah. And we know if a derivative of one function equals 0, this function equals the constant. Yeah. So the function y1 plus y2 equals constant function. Yeah. So we can write y1 plus y2 equals C1 constant. Yeah. Some C1 constant. Okay? Yeah? So what is C1? Yeah. What is C1? You can use the initial values to get a C1, right? So you plug in. Yeah. T equals 0. Yeah. Then you get C1 equals 150. Yeah. Yeah. Very easy. That means if you find one of the two functions, then the other function, you just use C1 minus y1, you get the second function. Yeah. So you only need to find the solution of one of the two functions. Yeah. All right. Then let's go back to our first ODE in the system. The first, we replace y2 function by C1 minus y1 function. Yeah. So then we eliminate y2 in the first equation. So in the first equation, you only have one unknown function, y1. Yeah. And we know how to solve it. Right? We know how to solve it. Yeah. So by our module 1 method, we can find a solution. y1 equals 0.5 C1 minus C2. Yeah. We need to determine the second constant, C2, times e to the negative 0.04 t. Yeah. Yeah. All right, so yeah, so then y2, yeah, we use c1 to minus this y1 function, so we get a y2 expression. Yeah. All right. Yeah. But the next, before we do the last step, we need to determine c1, c2, right? So using the initial conditions, yeah, c1, c2. Yeah. All right. So here, yeah. Yeah. Because it's pretty easy, I skip that part. C1 150, C2 75. Yeah. All right. Then, so we have the expression of the solution. The last step, we need to determine that T1 point. Yeah. So that's just another step of calculation. Yeah. Here I skip it because it's very easy. Yeah. I just skip it. Yeah. This is the old method. Yeah. Yeah. Actually, this method is not very good. Yeah. Why? Yeah. If we look at this old way, why it is not good? Because this method relies on some special property, right? Yeah. So this one you can do the cancellation easily, but in the general case, you cannot cancel out the terms easily. Yeah. So in general situation, if you apply this way, it could be pretty messy. Yeah. The calculation pretty messy. So it's not a good way. Yeah. So in the general situation, we want to use some systematic, way. Yeah. Although we need to do calculation, but we want to use some formula to do the calculation. Yeah. All right, so let's move to the new method, new solution. Yeah. For the new solution, yeah, so same equations, linear system, yeah, but we write it in the matrix form. Yeah. All right, yeah, so the y vector prime, then the coefficient matrix, yeah, very simple, yeah, so then y vector, unknown vector, yeah, and it's a homogeneous linear system because there is no g vector. Yeah. G vector, okay, g vector is 0. Yeah, all right. So to solve this one, this is our A matrix. Yeah. Then remember the characteristic equation. We need to solve the characteristic equation first. Yeah. So what's the characteristic equation for this matrix equation? Yeah. Remember last time we defined this determinant of A minus lambda times I2 matrix. Yeah. So that's this one. Yeah. Then by you know how to calculate determinant, right? Yeah. 2 by 2. Determinant of 2 by 2. Yeah. So you do the cross product. Yeah. Yeah. The first term, yeah. The product of two entries in the main diagonal. Yeah. That's the main diagonal. Yeah. Then minus the product of two entries in that what's that? Is there any name for the diagonal? Yeah. Yeah. So, yeah, but not main diagonal. So another diagonal. Yeah. Yeah. Slant. Yeah. I saw the name before. Yeah. Yeah. Yeah, but not subdiagonal because subdiagonal the meaning is different. Yeah. All right. Yeah. So we find the solution. Two solutions for lambda 1, lambda 2. Yeah. The first lambda equals 0. Second lambda equals negative 0.04. Yeah. All right. But after that, so what's the next step? After that, there is another important step. Yeah. So this is the first step. Yeah. Another important step. Yeah. So the concept, we need to learn another important linear algebra concept. Yeah. All right. So that's these two special functions. Yeah. So let's write. These two lambda values correspond to these two special functions. Yeah. Yeah. But the next step we need to do. Because our goal, we want to represent the general solutions, right? The general solutions. Yeah. How to represent the general solutions? Yeah. So remember, we need to find a basis for the solution, right? Yeah. The basis is formed by two linearly independent vectors. Yeah. So we need to find two linearly independent vector solutions for the original equation. So this is the original equation. Yeah. But our goal here, we need to find two linearly independent vector solutions for this equation. Then we can use these two vectors. We can write the general solution. But we need to find these two vectors one by one. Yeah. The first vector corresponds to the first eigenvalue. Yeah. So here, I haven't talked about the concept eigenvalue. Yeah. Eigenvalue. Yeah. Here, we need to use the linear two important concepts: eigenvalue, eigenvector. These two concepts here. Yeah. Eigenvalue. Yeah. So here, eigenvalue, right? The lambda. Eigenvalue, eigenfunctions, eigenvectors. Yeah. All right. Yeah. Yeah. And here, these two functions. Yeah. Yeah. All right. Eigenvalues. Yeah. Yeah. So we found these two eigenvalues. The question. How to find a non-trivial, remember? Non-trivial solution. Yeah. This equation has a trivial solution, right? Yeah, but we want to find a non-trivial solution for this linear system. Yeah. All right. Yeah. So this is our original equation. This is not our, yeah. All right. Our original equation, we use our original equation, we can derive this equation. So remember our original equation, y prime, so here, the vector, equals a times y. Okay? All right. Yeah. All right. And so here, so remember, so last time we also derived, y prime equals lambda y. If your y, if you use your solution vector, okay, y1, y1 or y2, here also use y1 or y2, y1 or y2, y1 or y2, so you have those two equations. So last time, so then we can write, because these two equations, we replace y prime part, so we get this equation. All right, and we know both y1, y2. If you use lambda 1 here, then your vector should be lambda 1. If you use lambda 2, then you should use the y2 vector. All right. So, and here in linear algebra, the lambda that satisfies this equation, we call it this lambda, eigenvalue of the matrix A. So that's the concept in linear algebra. Yeah. So what is one eigenvalue of a square matrix? Yeah. Here our A is a square matrix. So what is the eigenvalue? Yeah. Because when you talk about eigenvalue, the matrix should be a square matrix. Yeah. Yeah, because you need to calculate determinant. So the matrix must be a square matrix. Yeah. All right. Yeah. So that is the eigenvalue concept. All right. Now, you want to find a non-trivial Y solution. Yeah. That non-trivial Y solution, we give it a name we call the eigenvector, corresponding to one particular eigenvalue. So it's an eigenvector concept in linear algebra. Yeah. So here we need to calculate. Yeah. So we find two eigenvalues first. After that, we need to calculate two eigenvectors. Yeah. And these two eigenvectors form a basis of the solution. So then we can use these two vectors. We can write a general solution of this linear system. Yeah. All right, so next slide, let's do the calculation. Yeah. All right, eigenvalues and eigenvectors. Yeah. How to find eigenvalues? Yeah, we just did it, right? The determinant, we calculate the determinant. Yeah. So we start, this is the equation. The starting point this is definition of the eigenvalue. Okay, when we start, we use the definition of the eigenvalue, this equation. Yeah. But how to calculate it? Yeah. Determinant. Yeah. Yeah. This equation must have a non-trivial solution. Yeah. So remember, I gave you one important basic theorem in linear algebra last time. Yeah. Under what condition a linear equation has a non-trivial solution? Yeah. Yeah. So that is when the determinant of this matrix equals 0, then it has a non-trivial solution. That's what we learned last time. Okay. All right. Yeah. So it's an equation. Yeah. So lambda unknown. Yeah. But we can solve this equation for lambda values. Yeah. So we just did it. We find two roots. Yeah. Eigenvalues. Yeah. Next question: how to find the eigenvectors? So let's do the calculation one by one. Yeah. The first time we plug in the first eigenvalue lambda 1 into our original equation, the starting point. Okay? Yeah. The second time we plug in lambda 2 into this equation to find the second eigenvector. Yeah. All right? Yeah. For each eigenvalue, there is an eigenvector. Yeah. Here. Yeah. Yeah. In our current matrix equation. Yeah. All right. The first eigenvector, we assume, yeah, so here this notation, x sup parenthesis 1, yeah. We assume this is the first eigenvector. It's unknown. We need to find it. Yeah. So this vector is unknown. Yeah. We need to solve this equation for the first eigenvector. Yeah. How to solve it? Yeah. So we write the term at one side of the equation and factor out the eigenvector x sup 1 eigenvector out. Yeah. So this matrix is known, right? Yeah. The matrix inside parenthesis 2 by 2 matrix. It is known. Yeah. Lambda 1 value is given, so it's a known matrix. So given, if we know that matrix, can we find a non-trivial, non-zero vector here. Our goal, you need to find a non-zero vector that satisfies this equation. Okay? Yeah. And that non-zero vector must exist. Yeah. Yeah. So we know before we work on it, we know that non-zero vector must exist. Why? Yeah, the reason is very simple, because this condition holds. Because we find lambda 1 from this equation, this equation implies that the non-trivial solution for this original equation must exist. So that's why we have the confidence. Yeah. So we can find the eigenvector. All right, so let's do it. Yeah. All right, yeah, second, yeah, similarly, second, so that equation, yeah. So let's do one by one, okay? Yeah. The first time x sup 1, second time x sup 2. Yeah. How to solve a homogeneous linear system? Yeah, here. Yeah, so let me, although it's very simple, yeah, but here, so there are some, basic way we use to calculate. A matrix, all right, lambda 1 is 0, right? Yeah, so the lambda 1 times I2, that's 0 term, okay? Yeah. Yeah. Lambda 2, 0.04, yeah. Yeah. So we need to solve two homogeneous linear system. Okay? Yeah. The first homogeneous linear system for the first eigenvector. The second homogeneous linear system for the second eigenvector. Okay? Yeah. It's pretty simple. Yeah. But here, I need to give you a simple method to find the eigenvector for each equation, each homogeneous linear system. All right, so let's do it in the next slide. Yeah. First homogeneous equation. Yeah. In the first homogeneous equation, you can see if you compare the first row vector and the second row vector, can you see some special property there? The first row vector and the second row vector. What is the special property? Yeah, there is a simple special property there, right? Yeah. Yeah. Yeah, so because it's very simple. If you multiply -1 to the first row vector, you will get second row vector. Yeah. The difference, yeah, just a constant multiplication, scalar multiplication, scalar constant multiplication, -1. Okay? In that way, we say, in linear algebra, we say, these two row vectors are linearly dependent. That concept. They are not linearly independent, right? So these two vectors, two row vectors, linearly dependent. Linearly dependent, not linearly independent. Okay? Yeah. So here you work on two linear equations, right? Two linear equations. But these two linear equations, their coefficient vectors, are linearly dependent. What does that property tell us? Linearly dependent vectors. That property tells us you only need to solve the first linear equation. That's the first linear. The second one, because it's linear dependent, it has no contribution. Yeah. The second row vector you can cross out, because second one you just multiply -1. Both sides of the first equation you get a second one, right? So you do not get any new information from the second equation. Yeah. The first equation, linear equation, provides all the information you need. You don't need a second linear equation because linearly dependent. Yeah. Only when you have a linearly independent vector, the relationship, two vectors linearly independent, then the second equation provides new information. Okay? Yeah. Linearly dependent, so no new information provided from the linearly dependent equations. Okay? All right, so here. Then we only need to solve the first equation. Now, to solve the first equation here, because it's a simple equation, we can use our observation to find x1 value, x2 value. You want to try two simple values to make the equation hold. Yeah. Two simple values So the simple solution, x1 equals 1, x2 also equals 1. 1, 1, you put there, these two numbers adding together equals 0. Yeah? So that's the, your first solution. Yeah. All right, so the second one, the second equation, now, can you see the first row vector, second row vector, they are also linearly dependent, right? Yeah. Because exactly the same. Yeah. So the second one, you can easily agree the second equation does not provide any new information, right? Yeah. You only need to use the first equation to find the eigenvector. You do not need to use the second equation, right? Yeah. Redundant, right? Things like redundant. Yeah. Yeah. All right? Yeah. So then, by observation, what two special values you can try. So when you choose two special values, you want to choose as simple as possible. Okay? Yeah. So if 1 you put here, then -1 should be at the x2. Yeah. So that's a vector, right? So one special vector. Okay? All right. So you can write out the two eigenvectors easily. The first one, the vector 1, 1. Okay? Both positive ones. Second eigenvector 1, -1. Yeah. So you get two eigenvectors. Here, when you choose, you want to choose as simple as possible. Because actually, if you multiply some constant c, it's also eigenvector, right? So any constant c1 you multiply, any constant c2 you multiply to it, yeah, it's also eigenvector. Yeah. Because we have freedom to choose arbitrary constant vector c1, c2. Why not we choose the simplest c1, simplest c2? Yeah. That's one. That's one, the simplest. Okay? Yeah? Yeah. All right. So now, in this way, we find two eigenvectors for our coefficient matrix, capital A. Yeah. So we are ready to write a general solution. Yeah. So the last step. Yeah. Right. And corresponding to the eigenvalues, we have that, E terms we need to use to write our general solution. Yeah. Yeah. All right. The general solution, y equals c1 constant times the first eigenvector, yeah, x sup 1, times e to the lambda 1 t. Yeah. That's the way we use the first eigenvalue. Okay? All right. Then c2 times the second eigenvector, then times e to the y2, lambda 2 t. That's the form of the general solution. Okay? All right. Yeah. Yeah. And if we use this structure of the general solution, yeah, it satisfies our original equation, linear system of ODE. Yeah. Because we can verify easily. Yeah. So here we want to verify a little bit. Yeah. Okay. Yeah. Let's take derivative. Yeah. All right. Yeah. Take derivative first. Yeah. When you take derivative, yeah, because so here when we take derivative term by term, right? The first time the derivative on the first term, the second time the derivative on the second term. But when you take the derivative of the first term, the constant part, we do not need to do anything, right? Constant part, we can factor it out. Yeah. The eigenvector, the first eigenvector, x sup 1, it's a constant vector. So we can also take it out of the, inside function. Yeah. Then we only need to take derivative on that e function part. Yeah. All right. So we do the verification. Left-hand side, y prime, derivative of the first term, we only take the e function derivative, so we get a lambda 1, and then keep this e function part. Chain rule, right? Simple chain rule. Yeah. Similarly, the second term, C2 times lambda 2, yeah, x, the second eigenvector, then e to the lambda 2t. Yeah. That's a derivative. We plug in, so the left-hand side, we get this form. Yeah. Then, let's calculate the right-hand side. The matrix A, capital A times general solution expression y. Yeah. All right. Yeah, because we find our eigenvector from this equation, the first eigenvector. The second eigenvector from that equation. So when you multiply this A matrix, we need to use these two equations. Yeah. All right. So right hand side, A times y vector. So we plug in the specific form of the y vector. Then you multiply, okay? Yeah, multiply through. Yeah. Yeah. All right. Yeah. C1 scalar, so you can, put it in front of the matrix multiplication. Yeah. So A times, scalar, you can move it to the first. Yeah. All right. So the second one, C2, yeah, you can move to the front. Yeah. All right. Then this time you need to apply these two equations. Okay? Yeah. These two equations. Yeah. All right. So then you apply the, argument, because it's a special, the vector has the special property. So you replace the matrix A times x sup 1 by lambda times x sup 1. Yeah. And the second term, you get that. Yeah. Now you compare with the right-hand side, exactly the same. Okay? Yeah. So they are the same. So we verify it. Yeah. So it tells us, yeah, any solution in this form satisfies the original equation. Okay? Yeah. All right. Yeah. So, but that's the homogeneous case. Yeah. Yeah. So when you solve a homogeneous linear system of ODE, you use this way. Okay? Yeah. But after you find this general solution, you are done. Okay? You do not need to do verification. The verification we only need to do once. Yeah. So we know it's correct. Yeah. So then later when we solve the word problems, then we won't do the verification. Yeah. All right. Yeah. So finally, the conclusion. Yeah. The general solution for this problem. Yeah. So we can write C1, the first eigenvector, times C2, the second eigenvector, then that corresponding e functions. Yeah. Yeah. So that's the final solution. Yeah. All right. Yeah. So we solve the first problem. Yeah. All right. Yeah. So yeah. So we're doing pretty slow. So we use up our first half time. Yeah. We have one example for the second half. Yeah. But that example we can move a little faster. Yeah. Because we are familiar with the whole process. But the second example, we need to solve a non-homogeneous linear system. Yeah. So there is something new. There is that G vector. There is, when we solve the system, y prime equals a times what plus G vector, this G vector is not equal to 0. Okay? Yeah. So we need to, but we do two steps. The first step, the homogeneous part, we solve it. Yeah. After that, we need to solve the particular solution using that G vector. Yeah. So there is something new. Yeah, we need to learn. Yeah. All right, after the break time, so let's do that second example. Yeah. After that, we will move to part B. Yeah. All right, so let's take a 10-minute break.